All right, so today we are going to talk about double replacement reactions. These are reactions that create a precipitate. And so precipitate is just a cloudy solid that won't dissolve in water, okay? So the way that you're going to be able to tell that something is a double replacement reaction is that the two ingredients will be compounds. So you'll have two ionic compounds, positive ion, negative ion, and then another positive ion, negative ion coming together. And so whenever that happens, it's going to be a double replacement reaction. In a single replacement reaction, you had an element in a compound, and the element replaced the compound. Sorry, the element replaced one thing in the compound. Well, here we have two compounds, and all they're going to do is sort of trade partners. So if you look at the model here, A would be our positive ion, X would be our negative ion in the first compound, so we have positive, negative. B would be the positive, Y would be the negative in the other compound. And if you just have A and B trade places, then A would now be paired up with Y, right, because it's trading places with B. So A would be paired up with Y, still positive, negative, because Y was negative. And then B would be paired up with X. Again, still positive, negative. So this is double replacement. Now, the unique thing about this type of reaction is just like single replacement can end up resulting in a no reaction, so can double replacement. And here's why. When I have these ions trade places, the two reactants are going to be aqueous, and that just means dissolved in water. So, for example, AX, my first compound, might be NaCl aqueous. And what that means is if I have a beaker of this stuff, in that beaker, it's not going to be NaCl crystals stuck together. It's going to be a bunch of water and some positive Na and some negative Cl separated by water. That's what aqueous means. And then let's say my other reactant, my By, is, let's say, potassium iodide, also aqueous. And again, what the aqueous means is it's a solution, it's mostly water, and it's going to be positive potassium ions and negative iodide ions floating around in that solution. Okay? For this reaction to be successful, to be considered a reaction, when I pour the contents of these two beakers together, if those four ions, so when I say four ions, I mean 1, 2, 3, 4, if those four ions are still just floating around, dissolved in water, in that larger beaker once I've put them together, that's not really a chemical change. That's not a chemical reaction. That's just a mixture, right? Something else has to happen, okay? And what that something else would be is if when I put them together, so let's say this beaker now represents a larger beaker where I've poured both of these guys in here, okay? And the positive from, let's say, the Na from here and the I from here, if they come together and form a solid crystal or a bunch of solid crystals that won't dissolve, that does actually represent something that wasn't there before. That does actually represent a chemical reaction, a chemical change. Now the other ions, so like let's say what I've just drawn is NaI solid, okay? Now the other two ions that you would get from this, if Na paired up with I, then you'd also have K paired up with Cl. Well, those two are probably still going to just be dissolved. So those two would probably still be floating around separate from each other, and my other product would be KCl aqueous. And again, that just means that, let's say this is the K, and then this guy down here is the Cl. Those two are still just, floating around, dissolved, surrounded by a bunch of water. But if you get one solid product from this, then that means that you do have a reaction. So if NaI, for example, is a solid product, then this is a reaction. But if not, if both of them just are aqueous and just stay separate, and you just have four different ions floating around in this beaker, then that's nothing. That's not a reaction. So you would just say Nr. All right. All right, so then the next step is, well, how do we decide this? How could we possibly predict this? I mean, we could do the reaction in the lab and see if a precipitate forms, because a precipitate is just like a cloudy solid that won't dissolve, okay? But we don't always have the luxury of going into the lab and having the time to do that. So sometimes we just have to figure it out on paper. And that's where this chart comes in. So with our single replacement reactions, we had the activity series that could tell us whether something was a reaction or not. Well, with a double replacement reaction, we have these solubility rules, okay? And here's how it works. Let me give you another example. So let's say, in this example, we are going to try to react Pb NO3 2. So that's going to be lead 2 nitrate, and it would be aqueous. You don't really have to write the aqueous for the reactants, but they will usually be dissolved in water to start with. And let's say I wanted to react that with some sodium chloride. We just used sodium chloride, but we'll use it again. Okay, so the first step is to identify this as a double replacement reaction. And the way I do that is because I have two ionic compounds on the reactant side. So the only type of reaction that you would have that for would be double replacement. Okay, so the next step, once you decide it's double replacement, is to decide, okay, what's trading places, right? So what are my positive ions that are going to switch places? And so my positive ion is always going to be the first thing that is there in each compound, and that's going to be usually a metal, right? So Pb 2 plus and Na plus, those are both positive ions. They're going to trade places. All right, so if they trade places, that means that on the right side, lead 2 plus, and again, I know it's 2 plus because there was a 2 on the nitrate over here. Lead is a transition metal, so we only know it's charged by looking at the formula on the left. Okay, so we have Pb2 plus, and it's going to now be paired up with Cl1 minus. So my first potential product is going to be PbCl2, right? Because that would balance out those charges. So now I'll just erase the charges, put back my Cl, there we go. Okay, my other product, or potential product, because this could be a no reaction, would be Na paired up. So again, if we just have the lead and the sodium trade places, right? Now Pb is going to be paired up with Cl, and Na, sodium, is going to be paired up with nitrate. Okay, and in this case, Na is +1 and nitrate is -1, so we don't need any more subscripts. Now I do have to remember to balance this, but I'm not going to do that just yet because I'm not sure if this is even a reaction in the first place. All right, so how do we figure that out? Well, what we do is we look at our two products. So lead 2 chloride, I'm going to categorize this as a chloride, meaning I'm going to categorize it by the negative ion that's present. So the second thing. And so what I'm going to do now is I'm going to look at my solubility rules up above. And what this tells me, what this table tells me, is what is able to be dissolved in water and therefore will be aqueous, and what cannot dissolve in water and therefore will be solid. Okay? So you might know already that some things dissolve in water and some things don't, right? Like table salt, sodium chloride dissolves in water. So that it would be aqueous if water was present because it would dissolve. Okay, other things don't dissolve in water. So this chart is going to help us with that. Okay, so if lead 2 chloride could be categorized as a chloride, I'm going to look at the rule up here for the negative ion chloride. Now it shares the same rule with the other halides, so fluoride, bromide, and iodide. But there it is, chloride. And the rule says that chlorides are usually soluble, which would mean aqueous. However, there are exceptions. So you always want to check over here for exceptions. Silver, lead 2, and mercury 1. So lead 2 is an exception. And that's what this is, lead 2. So if lead 2 chloride is an exception to the rule, and the rule says that they are generally soluble, then that means that lead 2 chloride is not soluble. And so I'm going to go ahead and say that my PbCl2 would be a solid, which means it would be a precipitate, which means this reaction does happen. Because remember, we have to have one solid product in a double replacement reaction. Now my other product doesn't really matter because once I've identified a solid, the other one is pretty much automatically going to be aqueous. But just to practice using our rules, if I categorize this thing as a nitrate and I look up my rule for nitrates, it's the very first rule. It says basically nitrates are soluble and there are no exceptions. So every time you have NO3 in a compound on the product side of your double replacement reaction, you can automatically write aqueous because they will always dissolve. Okay? And by the way, you don't have to memorize these solubility rules. You will always be given access to them. Okay? So this is a reaction because we had one solid product, and that's what we need. We need one solid product. Otherwise, if they were both aqueous, it would be a no reaction. So I will go ahead and balance the equation. So see if you can go ahead and do that real quick. Maybe pause for a second. Okay, so hopefully you found that the nitrates maybe needed to be balanced with a 2 out in front of sodium nitrate because you had 2 nitrates on the left, which means I now need to balance both sodium and chloride with a 2 in front of sodium chloride. Okay, let's try another one. Let's try K2SO4 plus MgNO3 2. So first of all, hopefully you'll recognize this as double replacement because it's 2 compounds, specifically 2 ionic compounds, coming together. So see if you can go ahead and pause and decide what is going to trade places and what your potential products would be. Okay, so hopefully you decided that the positive ions are potassium and magnesium and that they would trade places, and that would give you potassium paired up with nitrate, which would just be KNO3 because we have +1 and -1. And then my other product would be magnesium paired with sulfate, and magnesium is +2 and sulfate is -2, so that's also 1-to-1, so we don't need any further subscripts. Okay, so those should be your products. And by the way, the order that I wrote them in doesn't matter. So you could have put magnesium sulfate and then potassium nitrate as well. Okay, so see if you can use the solubility rules and decide if this is a reaction. So did you get a solid product or are they both aqueous? Okay, so hopefully when you looked these up, you looked up nitrate and found that, again, that all nitrates are soluble. So that should mean that KNO3 would be aqueous, right? Soluble means it's going to be dissolved, going to be aqueous. Then your magnesium sulfate, well, most sulfates are soluble. There are exceptions to that. There are 4 exceptions, but magnesium is not one of them. So magnesium sulfate would also be soluble. So you're going to say AQ. And of course, what does that mean? Well, if both products are soluble, then that means we have a no reaction. And we don't need to balance it because it doesn't really happen. It's not a reaction.